our seminar 10 years before we even came up with the idea of having a seminar. So he he of course gives a talk with the original copyright, completely on topic, or on topic that this is not possible. And no, to connect with the previous talk, I think he will, in a sense, frame how maybe autocatalysis can indeed be counterproduce stability, so to say, be a source of instability or something like this in a context with mass action kinetics. So it's fully complementary, hopefully, to the previous talk. Please.
Yes. Yes. So yeah, first of all, I would like to thank Nicola and all the organizers for having this nice seminar. I mean, I was only brought to a notice a few months back, I think, when Nicola asked me to give this seminar. So thank you very much for having the seminar series and inviting me to give a talk. I think it's a pleasure to be here. So let me just start with a word of introduction. So I'm an assistant professor at the International Institute of Information Technology in Hyderabad in India. And most of my research interests are basically are towards analyzing the dynamics of reaction networks by kind of gauging the inherent structure of the networks without actually solving the ODs, but kind of guessing the dynamics of the network by analyzing its inherent structure. Right? So as the idea of the talk suggests, it resonates very well with the seminar talk. And as Nicola said, it's based on autocatalysis in reaction networks. So I guess most of this community is aware that, sorry, how do I? Yes. So the word autocatalysis stems, I think the first thing that comes to everyone's mind is this origin of life framework, right? How did life originate? And of course, you have this, I mean, just to kind of set up this discussion, you have this process of abiogenesis, a process by which living things can occur from non-living things. And the idea is that this is not such a simple process, right? It's not a single step process where just everything originated from non-living things, but rather a series of severely intricate and complicated steps that involve things like self-replication, self-assembly, autocatalysis, and the emergence of cell membranes. I mean, all these things have come in kind of tandem to generate life. And I think one of the things that has also been influential to generate life is this theory of hypercycles, I think, in which I think Professor Joseph Bauer has a series of papers in the last several decades. And so these have been analyzed to a large extent. And as in the line of the talk, the presence of autocatalysis networks is important for this mutual symbiosis and catalysis within organisms to kind of generate life, right? So that's the setup, right? That's the global picture of this autocatalytic networks. So to put this in context, I just wanted to say that my talk will be based on this paper, Autocatalysis in Reaction Network. So this is joint work with Manoj Gopalkrishnan, who was at TIFR at the time this talk, the Tata Institute of Fundamental Research at the time this work was being done. And it's kind of a bit of an old paper, but I think it kind of resonates well with some of the themes that the previous speakers have been speaking on. So I will try to give an idea of the talk in the context of reaction network theory. Right? So I will try to motivate this notion of autocatalysis from the viewpoint of reaction networks. So in the community of reaction networks, I think, how would you formally define a reaction network, right? So you can think of a reaction network as this tuple, S, R, where S is the set of species, R is the set of reactions. So for example, if you have this X plus Y going to Z and X going to 2X, you have X, Y, Z are the species, and these are the reactions, right? So very naively speaking, a reaction network is just a box of chemicals that kind of interact with each other. And the basic theme underlying this is to how do you model the dynamics of such reaction networks, right? So one way of viewing this reaction networks is you can think of reaction networks as directed graphs embedded in Euclidean space. So you can think of every reaction network as graphs. So for example, if you see in the figure, you have this reaction X goes to 2y. You can think of this as the vector -1, 2, because you have 1x being consumed. So that's -1 for X. and 2y is being produced. So this is representative of this vector -1, 2. And this y goes to 2x is representative of the reaction 2, -1, because 2x is produced, 1y is getting consumed, right? So this geometric way of thinking of reaction networks seems obvious, but is actually incredibly powerful. It's very, very powerful to think of reaction networks in this particular way. And as we shall see towards the end of the talk, that this viewpoint gives us some crucial insights. All right. So because you can think of reaction networks as vectors, and of course, as in the usual context of chemistry, you have mass action kinetics. So for every reaction, you have the rate constant associated with that reaction. And if we assume mass action kinetics, you know that the dynamics of the system can be written as follows, that you take this vector corresponding to that reaction, so 2, -1 corresponding to this reaction, y goes to 2x times the rate constant of this reaction times y of t, that's the reactant here. And similarly, you can do the same thing for the other reaction. All right, so -1, 2. The crucial point is that because it's mass action, the rate is proportional to the product of concentration of the reactants. So the only monomials that occur in your differential equation are those that occur from the reactants, right? So this is the basic setting. And what we are going to do now is to analyze the structure of this graph. Can you look at this graph, just this network without having to resort to this OD? Can you infer good properties? And one property that we'll explore is this presence of autocatalytic sets in this reaction networks, right? So that's the theme, that's the setting. So one very peculiar class of reaction networks is weakly reversible networks, right? And what weak reversibility means is that each reaction is part of a cycle. It means that not every reaction might be reversible. So for example, if you see the second subnetwork, this is a reversible reaction. But if you look at this first subnetwork, this is not, every reaction is not reversible, but it's part of a cycle, right? So you can think of this reversible network as a graph connecting of strongly connected components, right? So where each reaction may not be reversible. And the dynamical property that we would like to analyze is what is called as persistence. Okay, so let me try to explain a bit what persistence means. As the word suggests, persistence means that the ability to persist in solution or not go extinct, right? So we want species to not go extinct in solution. And another way of saying this is that for bounded kinetics, that for any initial conditions, you cannot have an omega limit point on the boundary. Or you can say that lim of xi of t is greater than 0 as t tends to infinity, right? So this is weaker than permanence, but at the moment, I'll just talk about persistence. And so these two come in tandem, weak reversibility and the idea that species cannot go extinct. Species can always persist in solution, have very intricate connections. And these two are related by a famous conjecture in reaction network theory, which is called the persistence conjecture by Martin Feinberg. It says that weakly reversible reaction networks, sorry, can you see my screen? I think. All right.
Yes.
Sorry. Yes. Weakly reversible reaction networks are persistent, right? So that's the conjecture. If you have weak reversibility, species cannot go to 0, cannot go extinct. This is a very simple to state statement, very simple conjecture. And however, unfortunately, it has resisted proof for more than 4 decades. For 40 years, we are not still have a complete proof of this conjecture. There have been several special cases that have been proved. So, for example, George Krachun, Fedor Nazarov, and Kassian have shown this, that in two-dimensional system, if you take just planar systems with 2 species, then 2 species weakly reversible networks are always persistent. And then it has been generalized by Kassian to 2-dimensional stoichiometric subspace, and then by Manoj Ezrahan to a certain class of networks which are strongly endotactic networks. Okay, so there have been some series of results that are aimed to prove towards this big conjecture, but not in full generality, only in some partial cases. All right, and I think Balash and Yosef also have a paper where they show that weakly reversible single linkage class are in fact permanent. Okay, stronger than persistent, but also persistent. Okay. But some of these things are just partial proofs towards this conjecture. A related conjecture to this is what is called as the global attractor conjecture, which says that for a smaller class of systems, which are complex balanced, which are smaller than weakly reversible, right? So there are systems that are weakly reversible, but may not be what are called as complex balance, which I will define in a minute, what it means to be complex balance. And it turns out that these systems are conjectured to be exceptionally stable. Okay, they have a well-defined Lyapunov function. They have the steady states are locally asymptotically stable and conjectured to be globally stable, right? So what does it mean by complex balancing? But it just means that for any vertex of your reaction network diagram, the net flux that flows out of any vertex. So I choose a vertex S0. The net flux that flows out of S0 should be equal to the net flux that goes into S0. So what you see on the left-hand side of the equation is the net flux that goes out of S0. And what you see on the right-hand side is the net flux that goes into S0, right? So if these are balanced for every vertex, then you call the system complex balance. And you just need one last piece of terminology before I move on to this autocatalysis sets, is that of a stoichiometric compatibility class, right? So given any initial condition, the stoichiometric compatibility class is an affine translate of the subspace corresponding to the reactions, right? So what is this S? S is the span of your reaction vectors. So for example, if these were my reactions, my reaction vectors are 2, -1 and -1, 2. The span of these vectors is the whole R2, the whole real plane in 2 dimension. So S is the span of these vectors, and X star is any point in the positive orthogon. So if I take an affine translate of S with this point X star, then I call it the stoichiometric class. So this is an invariant polyhedron, which means that once a trajectory is in here, it stays inside this polyhedron. All right. So given this terminology, then we have this biggest conjecture, which is called the global attractor conjecture, which says that for complex balance systems, there exists a globally attracting equilibrium. And again, this has been incredibly hard to show in higher dimensions. And we now have a proposed proof of this conjecture in full generality in all dimensions. Okay. So that was the setting. So I want to talk about these properties of persistence and global attractors in the context of autocatalytic sets, right? So where
Excuse
is the...
me. Is this proof considered correct by now, or has it been repaired? Or
Okay,
can you tell me
the
just yes or no, the current state? I don't want to interrupt long.
yes, the proof is still being written, so it's not yet being
Okay.
written. Yeah, it's not
Thank you.
it's not
Okay.
completely written. So there are parts of the proof that have not been written.
Work in
So
need of progress.
yes, yes.
Thank you.
Yes. So yes, this is a question that I often get asked, but so yes, it's still work in progress for many years. Yeah, so it's because it's too complicated to write down several things, I think. So what's my interest? So what's the interest with this autocatalysis networks is this special case of this persistence or global attractor thing, which was proved by David Angeli at Imperial College, Patrick Delinier, and Eduardo Sontag, right? So what they were able to show is that if you have weakly reversible networks and you don't have critical siphons, I'll explain what critical siphons means. But if you don't have these objects called critical siphons, which are related to these autocatalysis sets, then the dynamics is persistent. Okay, so what it says is that if you have weak reversibility in a network, and if you have absence, if you can exclude these objects called critical siphons, then your dynamics is persistent. So in some sense, yeah.
No, sorry, is this always in mass action setting, or in general, or more in the in general setting? This paper.
This paper was in the mass action setting, I think.
Okay.
Yes. So essentially, the obstruction to proving the persistence conjecture comes from critical siphons, and I'll explain what these mean. So what's a siphon, right? So as I said, in chemistry, you have a set of species. When would I say that a set is a siphon, right? So a set is a siphon if it is zero initially, then it remains zero forever, right? Or in other sense, I can say that it's a set of species that corresponds to the zero coordinates of a state. So let me explain this with an example, with a well-chosen example, right? So I'll be choosing some guinea pigs in my talk, which I will again and again use the same networks to kind of elucidate different definitions. So for example, consider this network. X goes to the empty set. Y goes to X plus Y. So in this case, X is not a siphon, right? Why is X not a siphon? Because if I put X to 0 here, if I just make X 0 here, I can produce more X using Y, using some non-zero Y. So if X is 0 initially, it won't remain 0 forever. However, if I put Y to 0, then Y is always 0, no matter, you cannot produce Y from any reaction in this network. So therefore, Y is a siphon. And the set XY is also a siphon, because if I put the concentrations of X and Y both to 0, then they remain 0 forever, right? But not X. So X is not a siphon, but the remaining sets are siphon. All right, so that's what a siphon means. And these siphons are essentially chemical switches, right? You can think of, in chemistry, you can think of them as, you can think of them as chemical switches, because they are dynamically invariant once they're absent. So if they're absent forever. There is no way you can bring them back. But what I said before is if I don't have critical siphons, then I'm persistent. Of course, if you don't have siphons at all, then you're persistent, obviously, because there are no siphons, then you're persistent. But a weaker condition is this notion of critical siphon. So I will explain what it means to be critical, right? So the sets that produce this obstruction to species being persistent is this very special siphons, which are called critical siphons. So a set has to be both a critical and a siphon to be a critical siphon. And this is the hierarchy, is that this is going to produce what I will later define autocatalytic sets in the framework of these networks. Okay, so that's the idea. So, okay, so what is critical? Okay, so what is critical? I mean, what it means is that, so let's take the span of our reaction vectors, right? That's the linear combination of all vectors in space. A set is critical if I take this vector. So let's say T is my set. Let's say X, Y, Z is my set. I put those coordinates to 0 that belong to T, right? So if I take a set T, I only put those coordinates to 0. And for the remaining coordinates, I put whatever value I want, positive, negative, 0, whatever. And if I can take the affine span, if I Z plus the span of the reaction vectors, if I translate my subspace with this point Z, can I reach a positive point? If I can reach a positive point, then I call my set critical. Okay, so let me explain this with a well-chosen example. Imagine you have this network, X goes to 2Y and Y goes to 2X. So your reactions are these vectors. These are your reaction vectors. So the span of these vectors is R2, right? The positive, the real plane. And the point is the set XY is critical because if I put the concentrations of both X and Y to 0, so this is 0, 0, I can reach the positive point by using a span of this reaction vector. So I get 0, 0 plus, I just take this reaction vector, minus 1, 2, 2, 1, and I reach this point 1, 1. I mean, the point 1, 1 is not important. If you reach any positive point, then you're fine. So geometrically, you can think of this as, imagine these are blue are your reaction vectors, and you start from the origin, and you take a translate, and affine translate of this vector 2, minus 1, this red dotted line that goes in the negative ortho. And then you again take a translate of this vector, minus 1, 2. That's this other red dotted line, which is parallel to this line. So by taking translates, by taking spans of your reaction vectors, you're able to get to positive concentrations from a boundary point. Okay, so that's in one sentence, that's the summary. A set is critical if you're able to reach something positive from the boundary by using reactions, okay, by using the span of your reactions. And here is one of our main results, that if you have critical siphons, a set which is both critical and siphon, then you generate autocatalytic sets. Okay, so that's one of the main central results of this paper, that if you have critical siphons, then they are chemical switches. They generate what are called as autocatalytic networks. And so what's the autocatalytic nature here? So this is again in the theme of this series, that what's a catalyst, right? So our naive notion of a catalyst is that it's something that alters kind of the rate of the reaction without actually taking part in it. Or for example, it switches off a pathway in its presence and switches of the pathway in its absence. So if it's present, then the reaction, the pathway goes through, but if it's absent, then it doesn't go through, right? And what I mean by a pathway is essentially not just a reaction, but all translates of this reaction. So I can add quantities to both the same quantities to both reactants and products. That's what I mean by a pathway. Okay, so let me explain this with an example. Imagine that I have a pathway that goes from X plus Y to Y plus Z. Then Y is a catalyst if there is no pathway from X to Z, right? So you can only convert X to Z if Y is present. But as soon as I take away Y, then there is no longer any reaction that goes from X to Z, right? That's the notion of, this is what I call an autocatalytic set. Okay, this is a catalytic set because this catalyst Y, it initiates the conversion of X to Z. But when I take away those Y, then there is no such reaction pathway. So this can be mathematically formalized as saying, if I can have a pathway from Y to Y prime, but I take away the common species from Y and Y prime, if I take away minimum of Y prime, that's the common set of coordinates from Y and Y prime, then there is no pathway from Y minus min of Y prime to Y prime minus min of Y prime. So this is what I call the autocatalytic / catalytic sets. And our main theorem is that if you have a critical siphon, then you always have this kind of autocatalysis in your network. That is the main theorem, that whenever you have critical siphons, then you have autocatalytic sets, or this network is autocatalytic. What that means is that if you don't have autocatalysis in your network, there are no critical siphons, and hence the dynamics is persistent. So absence of autocatalytic sets guarantees that species cannot go extinct. So that's the main theorem. That's the one line kind of idea of this whole talk in the theme of this seminar series. Absence of autocatalysis in the network implies that species cannot go extinct. Okay, so but let me explain why. So that's the point. So this is okay. So let me first explain why this is true. So imagine that if you have just a network, let's say X goes to 2Y, Y goes to 2X. First, let me convince you that this set X comma Y is a siphon. Why? Because I simply put X and Y to 0, then they remain 0. I cannot, if X and Y are 0 initially in this network, I cannot produce X and Y from this network. And it's also critical because of the previous reason, because of the slide that I just showed, that if I can reach from origin to a point in the positive orthant by taking the span of my reaction vectors, right? So it's a critical siphon. And if you add these two reactions, I mean, this is a simple example, but in more complicated examples, it is difficult to see that you can always generate such a pathway. That if you add these two reactions, X plus Y giving you 2X plus 2Y, then you get this pathway. And the common variables in this pathway are X and Y. But if I take away the species X and Y from this pathway, imagine removing both X and Y, then I get empty set going to X plus Y. But you can never produce a reaction like this. Empty set producing X plus Y from this network. So the set X comma Y is a catalyst, right? Is an autocatalyst, in fact. And so that's our one of our main results is that if you have critical siphons, then you can always generate such autocatalytic sets. And for example, so why does this work? Like, what's the connection between siphons and autocatalysis, and how exactly this works? And so the basic idea is that the fact that it's critical gives you this pathway that increases the number of species, right? Imagine that you went from 0, 0 to a point in the positive orthant. So the fact that it's critical actually helps you generating this path that goes to the positive orthant. And the fact that it's a siphon switches off the pathway. Okay, so what I'm trying to say here is I have this pathway Y going to Y prime, where I increase the number of species in set T. That is the consequence of the set being critical. And the fact that it's a siphon that allows that prevents this reaction from happening, Y minus min of Y prime. So this very elegant decoupling of critical and siphons allows you to always generate such autocatalytic sets. And this is a big deal, and big deal in the sense this is very powerful, because what this means is that if you don't have catalysis or autocatalysis, you don't have critical siphon, because critical siphons implies catalysis, but no critical siphons implies persistence. It means, by the result of David Angeli, Patrick Linier, and Sontag, it's persistence. So all you need to guarantee persistence is to check that there is no autocatalysis in the network, and then you're done. So to show that any trajectory is persistent, it's a sufficient condition for showing that any trajectory is persistent is this very powerful tool that comes from Siphon theory, is to show that this network does not have autocatalysis. All right. So this is the central one-line theme, right? If I were to say this. So this is one of our main results. I think there is another result which I want to talk about in the next few minutes, which is, okay, so before I do this, I just wanted to explain the significance of this result, right? So what I now told you was a combinatorial way of seeing the dynamics of siphon. So what I said was, if it is non-catalytic, which means I always have this pathway y to y prime, but when I take away the catalyst min of y prime, I still have this pathway. What is the significance of this, right? So it turns out that this actually condition can be viewed from the language of algebraic geometry, right? So you can think of reactants and vectors as monomials, and you can think of the ideal formed by those monomials, right? The ring in the ring of real numbers. If it's chemical, then the ring of natural numbers. You can think of the ideal formed by the reaction networks, by the binomials of the reactants and the products. And if you can generate monomials in the ideal such that m minus n, m is a monomial in the ideal, m minus n belongs to the ideal. But if I divide by the GCD of these two monomials, m divided by GCD of this minus n divided by GCD, then that also belongs to the ideal formed by the reaction networks. This is what it means to be non-catalytic. So what I just showed, this powerful combinatorial way, has this interpretation in commutative algebra, in algebraic geometry, that if your ideal is what is called saturated with respect to the variables, then it's non-catalytic, right? So this algebraic approach to the persistence conjecture was done in series of papers by Len Adelman, the famous A in the RSA, right? And Manoj and co-authors, where they showed that if you have prime ideals, if a reaction network generate prime ideals, then the network is persistent. This was strengthened to saturated ideals, which is this catalysis thing, right? That if I divide by GCD, then it's still in the ideal. And then this was strengthened further to autocatalysis networks, which is the paper that I'm talking about now, right? So that's the series in which this has been done. So this is the significance of this result. So that's why it's so powerful. And the second part of the result, which I wanted to talk about, is more in the sense of, is this connection with computer science. So can you think of reaction networks in terms of programming languages, right? So the motivation of this work comes from this DNA molecular programming community, where reactions are viewed as programming languages for the synthesis of a desired behavior, right? And one work that comes right in this context is that of Petri nets, right? Because it makes this connection with process algebras and concurrent programming languages, right? So what I want to motivate is, can you view reaction networks as some kind of programming languages where you can take small modules of reaction networks, combine them, and analyze the structure of the whole network? So can you meaningfully compose different subsystems and analyze the result of the big subsystem? So that's this is just another result that I want to talk about. So to motivate that, I just need to introduce one small definition, which is this notion of self-replication, which is very relevant in the context of origin of life, that I call a set self-replicable, right? If a species self-replicate themselves. So if I have this network, X going to this, the guinea pig that I've been using, I can use this network to generate the following pathway: 2x plus 2y going to 3x plus 3y by using reactions in this network. And this is self-replicable because you generate more x using y. So 2x plus 2y goes to 3x plus 3y. So you generate more of x and y from this reaction. And drainable just means reverse, that you generate less of x and y. So 3x plus 3y giving you 2x plus 2y. So you generate less of x and y, right? And what I want to say now is, this is another of our main results, that if you have minimal critical siphons, then you can always generate these self-replicable and drainable sets. Okay, so what I mean by minimal is the smallest critical siphon. So if I have a set which is a critical siphon, but there is no critical siphon sitting inside that set, there is no subset of that set, which is the critical siphon, I call it a minimal critical siphon. And if I have such an object, then I can always generate these kinds of sets, right? For example, if I have this reaction, X going to Y plus Z, Y going to X plus Z, and Z going to X plus Y, then this is critical because if I put all X, Y, Z to 0, then they remain 0, right? And that's a siphon, but it's a siphon because if I put all three of them to 0, then they remain 0. It's also critical because there is a path from 0, 0, 0 to 1, 1, 1 by using the span of the reaction vectors. And moreover, no subset of this set is a critical siphon. In fact, no subset is a siphon. For example, the set YZ is not a siphon because if I put both Y and Z to 0, then I can produce Y and Z starting from X, right? The same holds for the set X comma Z. If I put both X and Z to 0, I can produce this from Y, right? So it's a minimal critical siphon. And the claim is that if you have such a minimal critical siphon, you can always produce what is called a self-replicable or drainable pathway. In this case, we produce a self-replicable pathway by adding all the reactions in this set, right? So it turns out that this result is not that easy to prove. I mean, not that trivial to prove. And it hinges upon what is called as this nice result in linear algebra, which I call the convex rank nullity theorem. It says that if you have a matrix like this, which is diffusive, which has negative elements on the diagonal and positive elements on the off diagonal, then if it's full rank, then the cone of the rows of this matrix either meets the positive orthant or the cone contains the negative orthant, right? It's this one of these duality results. So for some of you, this might remind you of Farkash lemma or Minty's lemma, but it makes a weaker assumption and produces a stronger result that the cone of the rows either intersects the positive orthant, in which case you produce a self-replicable set, or the cone contains a negative orthant, in which case you produce the drainable set, right? So that's the idea behind this proof. And so what's the significance? I mean, what's the point of saying all these things is that I want to think of minimal critical siphons as some kind of building blocks of CRNs, right? So just like you can understand the behavior of natural numbers by studying the nature of primes, right? Because each natural number is a product of primes. Or just like you have the fundamental theorem of abelian groups that help you understand the behavior of groups by understanding behavior of subgroups. The hope is that can you analyze the dynamics of the whole network by analyzing the dynamics, by stitching together the dynamics of each such minimal critical siphons, right? In some sense, are these minimal critical siphons the primes of this network, right? So that was the motivation. So to summarize, I think we have two things that we have shown. This comes to the end of the talk. One is that if you have these objects called critical siphons, then they generate these special autocatalytic sets. And you know that absence of autocatalytic sets is related to persistence in chemical reaction networks. And then this result about minimal critical siphons, which is quite relevant to people in the molecular programming community, right? The DNA computing community that use reaction networks to do computing. So this could be used as some kind of decomposition theorem for people in that community. So I think, yeah, that finishes my talk. And so actually, details about these talks are also written in a blog post by John Baez. So John Baez is a mathematical physicist at UC Riverside. He writes a blog called Azimuth, where he discusses quite a lot of stuff from category theory to reaction networks, and a lot of stuff about my paper has been kind of written in this blog by Manoj. So you can have a look at this blog if you're interested to know more about this paper. All right. So thank you so much again, Nicola and other organizers, Praful and Alexis, for inviting me to this seminar. And yeah, thanks very much.